History and Philosophy of Science in Princeton. He has been offered an almost endless list of academic honors, fellowships, grants, and memberships in scientific societies, among them, lastly, the Académie Internationale d'Histoire des Sciences. What is all the more impressive is that he has worked intensively in the development and the historization of computer programs like Unix, and that he belongs to the rare group of historians who bridge easily the Middle Ages with the computer age, and who are able to activate questions which one would not at first glance direct to the sciences, like gender. Perhaps his most successful book is on the mathematical career of Pierre de Fermat. Recently, he has undertaken studies on the history of measuring. Among these studies, charting the globe and charting the globe and tracking the heavens is to appear. Please.
One's always in suspense as to whether the technology will work. Let me begin, if I may, because you will have seen my abstract for this talk, by saying just pointing to what I'm not going to talk about. As Horst Bredekamp pointed out, the study of the visual imagery of scientific development in the 17th century has been a recent interest of historians of science, and I think has redefined some problems, especially with sketching. But one is used to seeing the finished plates of Vesalius's Fabrica. One's used to seeing those marvelous copperplate engravings of Robert Hooke's Micrographia. But what should be of interest to us is the sketches that we know Vesalius was making as he was anatomizing, the sketches that Hooke must have been drawing as he was looking through the microscope, the sketches that we know Galileo was drawing when he was looking through the telescope, working with the hand to train the eye as to find out just what it was seeing. It's a wonderful topic. I wish I knew something about it. I could talk to you on the subject. But that kind of sketching, that thinking with the hand, that thinking, trying to capture nature in a moment of its action, is also reflected in another form of sketching in the 17th century, which is sketching through models. Now, we've talked about models. Irving mentioned the Bozzetti that had really brought him into the field. Here we see an example of modeling from an early plate in Domenico di Fontana's account of moving the obelisk. Namely, these are demonstration models of other proposals for moving the obelisk, for lowering it, bringing it around to the front, and then raising it again. And what is striking about almost all these other models is that they could never have worked. They couldn't have worked because they would never scale up. For one thing, humans don't come that large, and humans are essential to the operation of these things. Secondly, most of these would have collapsed under their own weight had they actually been built to full size. And it's interesting that the two new sciences of Galileo starts off with the question of the scaling of models to full size, and the question of why machines in the large do not work as well as machines in the small. So one sees throughout the 17th century, and I'll come back to it, this notion of modeling, I call it modeling the large in the small. But there's another kind of modeling that's going on, and that's modeling the small and the large, that's trying to understand the world that can't be got at directly by the use of models and then reasoning down to the small. The great example of this is what I consider one of the great literary sketches of the 17th century, Descartes' Le Monde, ou Traité de la Lumière, which is the sketch of a philosophy of a new world of matter in motion, a radically reduced world in which there is only matter broken up into small pieces moving around in a constant vortical motion. And Descartes' argument is we can explain everything on the basis of those mechanisms if we get the right laws of motion, the right laws of interaction. It has to be a sketch. He doesn't know how to fill in the details. All he can do is rough it out. And here we see him turning to models in the large, that is, containers of balls to try to understand how a pressure of light might pass straight through a medium. He turns to the hourglass to show how the sand flows. Right? What he is trying to do here is provide analogies in the world of experience to get at the world below experience, indeed, the world that explains experience itself, that is, the model of his ultimate model of light explains how it is we see and have a perception of light. And here, for example, he uses mechanical models, here a pulley with several ropes, and here a mechanism which he's trying to show how light rays could cross one another in the way air would cross one another if people were blowing into various holes simultaneously. Right? Again, he's trying to explain ideas on the basis of experience, but he's trying to explain a world in the small. Now, as I said, Descartes' world is sketchy. It doesn't supply the details. He's not sure of what the mechanisms are, but in particular, it's sketchy because it lacks the mathematical structure and precision that he promised for his philosophy. This was to be a mathematical philosophy. And for that, he needed a mechanics that tied matter in motion to observable mechanisms that would give insight into the underlying structures of reality at the same time that one could test those insights by building mechanisms. And the figure most responsible for carrying this out is Christian Huygens. Now, Huygens is unusual for many reasons. One, I think he was a skilled draftsman and he drew a lot. And secondly, the editors of his papers made the wonderful decision to reproduce in the published version not redrawn diagrams, but the original diagrams. So these are all by Huygens' hands. Every drawing you see this morning, every drawing I show you was one drawn by Huygens. And Huygens worked in both directions. We have here a drawing he made on 20 January 1675. You may not be able to read that Greek up here, but you can read it there, Heureka. His father called him Mon Archimede, and Huygens apparently took it seriously, so all of his great discoveries are marked Heureka. This is the coiled spring balance for regulating a watch. This is his first drawing of that coiled spring balance and his first rough sketch of a mechanism. He then articulates the mechanism in two different ways. He tries a little counterbalance wheel there, and then finally draws these diagrams of the mechanism. Now, what happens here is really interesting, and we have a note. He said, I went looking for the clockmaker Isaac Thierry to build me a model. I couldn't find him at first, but when I finally found him, I explained it to him. He, hardly understanding it, could scarcely believe it was true. But he built me a model, and I took the model and left. Thierry then built another model and started to develop another model that was aimed at getting that mechanism into a watch and built a working watch. Thierry then claimed, when Huygens sought a privilege for this invention, Thierry claimed credit. Now, Huygens' argument was, but he barely understood what I showed him. Thierry said, what I understood what he was doing, I built a model. And clearly he did, because if Huygens showed him the sketch, Huygens must have taken the sketch and the model with him when he left, and Thierry was able to turn around and build another model. I think we have here a wonderful socio-epistemological problem. What is it that Huygens thought he was showing Thierry? What did Thierry have to understand? And what did each man not understand of what the other was doing? Now, I want to just raise that as an issue, but I want to get down to some other sketching by Huygens, and in particular, this question of how the mechanism becomes a working mechanism is, I think, a part of a whole new area of research we have got to carry out about the relations of scholar and craftsman in the scientific revolution. The last word has not even begun to be said about that subject, and it is encapsulated in this episode. Now, I want to talk about some fairly detailed stuff, in particular the mathematical structure, what it is that led Huygens to his Heureka. But I want to emphasize here the importance. There'll be a quiz on this in coffee break. the importance of this work, because what I'm about to talk about is going to get into detail, and you may wonder, well, gee, that's nice, but what does it have to do with anything? Huygens devoted his entire life to the building of a clock that was accurate enough, reliable enough, and strong enough to be used to determine longitude at sea. From his very first pendulum clock, in which he figured out how to hang a pendulum on a clock, through his discovery of the cycloidal pendulum, his work on the center of oscillation and the sliding weight to adjust the clock, and the various designs of marine clocks, the subject dominated his life. The subject is also a filter through which an earlier agenda of research passes and becomes a new agenda of research that leads out to classical mechanics. And it passes through this filter of Huygens' work on the clock. So that is the overriding importance of the details I'm going to be getting to. Now, Irving, is this scratched out enough for you? Irving has been complaining that no one has a sketch that shows some real rethinking. I would like to concentrate on this drawing right up here. So let's bring that up. Huygens wanted to figure out what the period of a simple pendulum was. So he began by drawing a picture of the pendulum. Moved, he says, through a very small arc, but it's drawn reasonably large in order that we can see what's going on mathematically. On that drawing of the clock, he then wants to compare the speed, the time of the fall through this arc with the time of the fall, free fall, through the radius, through the string length of the pendulum. So he starts the body off at K and lets it drop, and first thing he does is to draw here this line, a semi-parabola, which is the Galileo's parabola of velocities acquired in falling. And then he draws another curve here. And let's take a look at that curve, because he gives us a diagram for it. This is the parabola of fall, and this curve is so constructed that this line length is the inverse of this one. That is, what he's doing is essentially turning velocity inside out, inverting it to get the time that takes a body to fall at the speed that is acquired in free fall at that point. Now we go back to the diagram. Now, he's got another diagram. The problem is here that the body falling along the arc of the circle is not in free fall. It has to travel along the tangent, and that's going to affect its time of fall. So he computes what the ratio of the time is going to be, and he winds up drawing a curve out here that represents the time of fall of the bob along the pendulum arc. Okay, now he has a diagram out there, and this is the equation he winds up with, the relationship, which is a problem for him because Bx, Be, and Bd are all unknowns. They're all variable. And he has to be able to reduce this relationship. So, to reduce it, he concentrates first on these pair of curves down here. And he brings up another diagram, draws off to the side another diagram. It turns out that if the arc of the circle were in fact the arc of a parabola congruent to the parabola of fall of times, then the product of these two abscissas will be a constant times the arc of the chord of that circle. So he's able to reduce two unknowns to one if the arc of the pendulum bob were a parabola. So he says, well, let's assume for the time being that it is a parabola. After all, we're making an approximation. So back to the diagram. And now he says this has to be the arc of a parabola similar to this one, and he calculates exactly what that parabola is. That has now changed this relationship here to one that's more manageable, and eventually comes down to finding the area under this curve Now, this curve having been transformed to a form that he can handle mathematically, and for that, he has another diagram in which he is able to show, this is a reduced form, that is, some of the basic parameters have been left out, in which he shows that this area under the curve is to the rectangle here as the semi-circumference of the circle is to this diameter, or as pi. So he's back now. He has to make certain adjustments. But basically, that result allows him now to determine that as an approximation, the pendulum's period is a constant pi times the square root of the length. That's the equivalent form of it. Here's where it gets interesting. This is already a mathematical tour de force in terms of the mathematics of the period. But here's where it really gets interesting. This was an approximate relationship, and he asked, well, I would like a pendulum bob to swing out the same period no matter how high it rises, because this is going to be on board ship, and you're going to never tell which way it's going to roll. What would it take to make this exact? This relationship of those two curves, what would it take to make the parabola that I substitute for the arc of the circle not an approximation, but an exact relationship? To find out, he goes in, oops, I'm sorry. He goes in and unpacks the way in which he had arrived at the relationships in the first place. I can't go into the details. But basically, he's not misled to think, well, I'll just put the parabola for the arc of the circle. He rather unpacks how he got the various relationships that led him to want the parabola. Basically, he says, I have to have it so that BD, the normal, is to BC, the ordinate, as EC, a constant length, is to CF, which is this ordinate, to the curve itself, to the parabola. So what curve must this be in order that that ratio give me a parabola as the result? And then, no warning, he says it's a cycloid from its known tangent properties. And you go, how? Where? Where did it come from? Whatever made him think the cycloid? He's begun to draw one in here. Well, if you look at this diagram carefully, look what we got. You'll know this from Jean d'Ombre's picture. Here is your generating circle, and here's your outline of the cycloid. Cycloid, in a sense, had been staring at him in the diagram. And I want to argue that that's the hint he needed. The drawing had not, in fact, had anything to do with cycloids when he started. But he winds up in a sketch with the basic structure of a cycloid. One of the beauties of sketches is that they're not exact. They leave room for approximation. Sorry. Okay. Sorry, this is where I wanted to be. He now goes on then to redraw the diagram with the curve as a cycloid, and then reconstitutes his proof. And he is able to show then that if a pendulum bob is constrained to swing along a cycloid, then its period will indeed be independent of its amplitude. The question is, how do you get a pendulum to swing that way? And it turns out that if you take a cord and wrap it around a cycloid and then unfold the cord, always keeping a tangent to the cycloid, the curve you generate will be a cycloid congruent to the original. So if you want to keep a pendulum bob on a cycloid, you just build two cycloidal leaves at the point of suspension of the pendulum and let the cord wrap around it. As it does, it will pull the pendulum bob up onto a cycloid. So he's got his cycloidal clock, cycloidal leaves. Now, this work was done in the late 1650s. It led to various other kinds of work on the clock. I want to jump forward in time to the early 1670s. I think as he's working out the final version of his great work on the pendulum clock, when he discovers or he works out what the dynamic properties on the cycloid are that lead to this property of tautochronic motion. And he comes to the conclusion that a body, no matter where placed on an inverted cycloid, will take the same time to reach the bottom, is because the accelerating force on the body is proportional to its arc length from dead center. So the force to restore is proportional to the distance from equilibrium. That is the property of the cycloid. He believes it explains the cycloid's property of tautochronic motion. One of the first things he does is to go to the stretched string, which he knows to be a tautochronic mechanism, to vibrate evenly. And in a series of drawings, uses the cycloid as a model for analyzing the motion of the string. So what we have is mathematical modeling of tautochronic motion, trying to see if we can get a mathematical analysis of a known instance of it. The nice thing about this sketch is that this is supposed to be an inextensible string, and yet he wants to have a triangle in here. So the mathematics, the sketching, allows him to create, as it were, a virtual triangle to make counterfactual differentiations that he needs to carry out the mathematical analysis. A little bit later, within a year, he thought about that principle, that the force on the bob is proportional to the arc length. The force is proportional to the distance from equilibrium. He read Hooke and Hooke's announcement of the law of springs, ut tensio sic vis. That is, the greater the displacement from equilibrium, the greater the force to restore. And so now the spring, the leaf spring, the helical spring, and the coil spring become mechanical models of tautochronic motion, of which the cycloid is a mathematical example. And so we see now a series of experiments using springs. Let me back up for a second. Yeah, you see now a series of experiments in which he tries to apply the spring, and I've shown you the drawings. As he went from these drawings then to that little drawing of a coiled spring with balance arm to the mechanism for a spring-regulated balance. Now he goes in other directions at this time. Well, a few years later, he comes up with the idea of what he calls his tricord pendulum, which is a ring suspended with 3 cords, which you then give a twist to, and it will oscillate tautochronically. And he tries to work out the mathematics of that, and that requires understanding the curve that would be struck out by this point as the ring is twisted and rises, and you get a curve wrapped around the surface of a cylinder. And here he works out the dynamics of that, trying to show that the motion would be tautochronic if this curve were a parabola, and then he goes to work out the mathematics of that curve by now a standard trick. This is not a cycloid in this case. What he's doing is taking what would be a circle here and then expanding it in order to unfold the surface to see what the curve was, and to satisfy himself that though the curve is not in fact a parabola, it is close enough to a parabola down here to give him the motion he's looking for. So he's playing with various forms of motion, modeling mathematically, but always keeping the physical object in mind. And indeed, he built a conical a tricord pendulum mechanism to show that it would in fact work. Later on, he pursues what he calls the balancier marin parfait, the perfect marine balance, meaning a tautochronic mechanism that could withstand the rigors of sea. By this point, he has gone from the cycloid to this notion of what he calls incitation parfaite, perfect incitation. What he means by that is the restorative force is proportional to the distance from equilibrium, and now begins to sketch various mechanisms for which this would apply. And here he has the idea of you take a globe, you wrap a string around it, and you hang weights. In this case now, as you set it in motion oscillating, it will pick up weights as it swings to the left, and the amount of weight it picked up will be proportional to the distance that has been moved. So you have another example of incitation parfaite. But what is interesting here is to contrast it with the drawing of this with his original coil spring drawing. And you can again see these models in mind as he's thinking through the problem. This is the coiled spring. This is another version of a simple harmonic oscillator. He never uses that term. But this is a version of the simple harmonic oscillator, and you can see the design factor being continued. Here, indeed, he now takes the mechanism, turns it on its side, wraps the cord around a rod. You can see a clockwork beginning here. Here would be a support for the string, and here's the sketch of an escapement wheel. Only now what he's doing, instead of using chains, lifting weights, he's got cylinders immersed in mercury. Hydargire is this word. And they'll be raised and lowered, and by the amount they're withdrawn, the force will increase, and you'll have the same thing as you have the chain mechanism. And here, to make it even more directly applicable to a clock, he takes the mercury and puts it in a closed cylinder and adjusts the mechanism. He's thinking of the clock, but he's also working toward the mathematics. Here, his conical pendulum. This is working with evolutes. He has to constrain the curve of motion to a paraboloid back from the circle. Here he uses this motion of evoluted unfolding curves, such as the cycloid, but here he turns back to his newly discovered chain mechanism, sketching his way to a solution. Now, if I may, I'll just move very quickly. Another problem with the clock is adjusting it. And that's a problem of dealing with the fact that the simple pendulum of mathematical abstraction is a weightless cord and a bob where all of the mass is concentrated in the center. But real clocks have real bobs attached to real bars. So he has to work out the center of oscillation of a compound pendulum. This is his first drawing, simply using two weights and trying to figure his way through it. This is the more interesting. This is a derivation of the center of oscillation of a rod. And what he does, he breaks the rod up into individual pieces. On this side, we have a pendulum. This is a physical picture. He takes the center of gravity, measures it here, drops it through an arc. They will acquire speeds. At this point, he imagines all of the connections being loosened and each of these bobs being directed upward by a 45-degree plane to reach then the height it would reach given the speed it's acquired. We would say today, on this side, this is the curve of kinetic energy. The center of gravity of this curve has got to match, of this system of disconnected bodies, has got to match the center of gravity of the connected bodies, and that is what enables them then to figure out what the simple pendulum is corresponding to this compound pendulum. Now, what's important here is this shift, this interface between the physical picture, mathematical abstraction. To show you where it leads, here is proposition 41 of Newton's Principia. This is the physical orbit. This is the dividing line. This is the curve of forces. This is the curve of time. And these are auxiliary diagrams, the areas under which allow Newton to plot the position of the body on its trajectory at any given time under an arbitrary law of force. Physical picture, interface to a mathematical picture. One sees that being developed in Huygens. It is no wonder that Newton acknowledged Huygens, among all others, as an inspiration. What gets interesting from the point of what Jean Dromel was talking about is if we take this diagram and look at its next instantiation, there's Newton's physical picture reversed. Where is the mathematics? Where is the geometry? It's gone. No, it's not. It's changed form. It's now in the language of Leibniz's calculus, a language that I would argue allows another kind of sketching. It's the kind of sketching that allows you to play with concepts by algebraic manipulation, to move from work to energy by way of force and momentum, and to see how they play out with one another. One is pursuing another set of representations. The language of sketching changes. But this pursuit of mathematical models that allow one to talk about a world that one cannot reach, the world that one believes to underlie reality itself, to talk about that world in ways that one can then test against experience. So the model becomes an interface. The mathematics becomes an interface between those two worlds. What we see in Christian Huygens in particular, but I think this example could be multiplied if we only had the documents, what we see is that process beginning in 17th century. Thank you.